Hello and welcome to this video about determinant proofs. In this video we'll prove all of these results that are extensions of the multiplication theorem. Most of them involve raising matrices to powers of integers. There's a matrix commutativity proof and a similarity proof as well. So let's begin with the matrix commutativity proof, that it doesn't matter about the order of multiplication of two matrices, they will give the same determinant. So this is a pretty easy proof. We'll turn this expression into a product of two determinants. And since these values are either reals, rationals or complex numbers, then we can reverse their order of multiplication and still get the same value. Then we can reverse the multiplication theorem to get this expression, which proves part A of this theorem. Now to prove this power relation of matrices, and notice that we're proving it for n being greater or equal to 2. So we'll prove this using induction. We'll firstly prove it for n is equal to 2. We'll start with the determinant of a squared and then write it out as two a's multiplied together. It's necessary to do this bit of unsimplification. We can then use a past theorem to split this up into the product of two determinants. And then finally we can simplify this to be the square of the determinant of a, thereby proving it for n is equal to 2. The next step is to assume it true for n minus 1 and then show it true for n. We'll start with the determinant of a to the power of n and split this product up into a times a to the power of n minus 1. We can then break this up into the product of two determinants like this. We've assumed it true for n minus 1, so we can write the n minus 1 outside the determinant like this. And so we can simplify this expression to be this, because we're just adding 1 to the indice n minus 1. So we've proven part B of this theorem. Now to prove this part of the theorem, which involves finding the inverse of the determinant, or raising it to the power of minus 1. To prove that a number or matrix is an inverse is a bit different to other proofs. In this case, we have to multiply it both on the right and the left to show that it's an inverse. You should only need to multiply it on one side because the determinant is a scalar, but there might be matrices that have entries that aren't commutative. So we'll show it to be a left inverse first. We'll multiply it on the left by the determinant of a. We'll use a past theorem to gather everything under the one determinant function. This will give us the identity. And the determinant of the identity is obviously 1, so this is a left inverse. We'll show it to be a right inverse this time. And the working is almost identical to last time, so it's a right inverse as well, giving us a product of 1. So it's both a right and left inverse of det A. So it's an inverse of the determinant of a, so we've proven part C of this theorem. And this quantity is obviously an inverse of the determinant of a. Now to prove part D, that this power rule is true for all integers. In fact, we only need to prove this by induction in the reverse direction, which we can do now because we've proven it true for n is equal to minus 1. We'll assume it true for n plus 1, and then show it true for n. We'll start with the left-hand side and expand out the expression inside the determinant, using rules of exponentiation. Then we can split it up into the product of two determinants like this. We can use part C of this theorem to move the minus 1 outside the determinant. We can move the n plus 1 outside the determinant because we've assumed it true for n plus 1. Then we can add these exponents using the rules of exponents. We can use a past result that it's true for n is equal to 2 and work backwards to prove it true for all integers less than 2. So we'll write this down, that it's true for all integers less than or equal to 2. And we know from part B of this theorem that it's true for all integers greater than or equal to 2. So finally we can say that it's true for n being equal to any integer. Now to prove this result for similar matrices. Now to start this proof, this is the definition of similarity, that we can find a matrix P so that this equation is satisfied. We can apply the determinant function to both sides of this equation to get this. Then we can split this expression into the product of three determinants. We can then swap these determinants around like this because they're scalars. Then we can take the minus sign outside the determinant like this. And then finally we can eliminate these two determinants because they form an inverse pair, thereby completing this part of the theorem. Now to prove this result, multiplying a matrix by a constant c multiplies the determinant by c raised to the power of n, where A is an n by n matrix. So when we multiply a matrix by a constant, we're multiplying all of the rows of this matrix by this constant. So we're multiplying the determinant of this matrix by c n times, which is multiplying this matrix by c to the power of n. We can prove this a second way by bringing in the identity matrix like this. Then we can separate out the determinant into a product of two determinants like this. So this is what matrix Ci looks like. It's a diagonal matrix with all of its diagonal entries being equal to c. And the determinant of this matrix is c to the power of n. So we can evaluate this determinant, thereby getting the equation that we were after. So we've proven this part of the theorem and proven it twice. And finally, now to prove this part of the theorem, that we can take the square root sign outside of the determinant function like this. So we'll multiply this expression by itself and gather it into the one determinant. And these matrices multiply together to give us the determinant of A. So we've proven all of this theorem. And this quantity is obviously the square root of the determinant of A. So I hope that you found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to write anything helpful in the comments and to share this video. And thanks a lot for watching.